Good morning, everyone, for joining. For water security research group. Also introduce myself a bit in the presentation. Next, Professor Hadas Mamane and Professor Friedler and Asaf with us. I think we should give a brief introduction and his or her presentation, so we speak this. Just for the objective and the agenda, what we do here together in Spana, it's around between 10 now and I think it's about 30. That will have so quite a long time and to have a discussion. There is that I will introduce a bit approximately 30 minutes, a bit less, about IIASA and the water group in IIASA. So then what we're doing there, what we have, what we're actually looking for also. And on the colleagues here, they will basically bring some perspectives of some of the Israel-related water research. If there is more research about water in Israel, but this would be some kind of highlights parts of something that are doing. And we have also Eran here with us. So we hope that this IIASA presentation. It's not the speaker in this panel, but of course he can also contribute from his experience. Yeah, and the last stage after all the speakers will finish the presentations, we have some kind of practical questions for discussion, but the idea is to kind of come up with ideas or directions of collaboration between IIASA and Israeli researchers, Israeli PhD students, master's students, postdoc students, in water related or in beyond water related things. Any questions about the agenda? So is that. And I should share screen, I think. Just before I think we're recording the panel, so if anyone has a problem with recording the presentations, share screen. Just let's see. Okay. Also in the webinar. Whoever watched us or know for already online. Attendees. That's some.
It's the presentation.
Yeah, try. Okay. Good. I think it's on.
You can hide.
I see it's here. More and then add panel is floating into the report. Yeah, it's done. Okay. So what I'm trying to do in this bit less than 30 minutes ago is to give us all a kind of overview of IIASA water group research about water and water human interactions. So it's quite a lot of research done in this group. It's quite diverse research direction, and I would like to give this overview. We'll start with a bit about Aviv, who is this research water security research group, and an overview of the tools and models that we had and used. Some few examples of ongoing research projects, not all of them, but just a bit. And then opportunities for collaboration from our side. Thank you, staff. So basically, just to focus you on this one, slide we saw one of us this morning already. So this is the structure of IIASA, and they standardize 5 main research programs and strategic initiative program. And within it from our research group, so here within this biodiversity, you have to believe me that this is what it says, but biodiversity and natural resource program, we have also the water group here. So we are accompanied by a bunch of other research groups, each dealing with its own different aspect, different dimensions of the human or natural systems. And one of the goals of IIASA is also to kind of mix the research within this group to apply to system thinking approach and also observe the synergies between different dimensions of kind of different dimensions. In the water research group of 17 full-time equivalent researchers, some of them are researchers, some guest researchers, and some of them are PhD students and postdoc fellows. 2 Israelis, myself and Bonita, she's a postdoc, just an Israel postdoc, and she's about to finish our group. And we have also people from 17 different nationalities. Yes, it's quite diverse organization. People come from all around the world. The goals of the research, water research group, also diverse. So we developed this interdisciplinary approach for water issue, connecting different sectors, different scales, looking for global, regional, and also landscape or watershed modeling. We develop and use local, regional, hydrological, and hydroeconomic models for the aim. And we also are involved in developing scenarios, specifically water future scenarios, and this water extending shared socioeconomic pathways, and we have that clear implications. So there's climate change trajectories, and within climate change trajectories also how the society, how the economy is about to develop in the future. These two direction of development, two pathways go hand in hand and guided through modeling plausible trajectories for future water issues. Engaging with stakeholders for better planning and performance capacity development activities, doing modeling, model simulation games. Yeah, okay. Go to the slides. So some of the tools that we are working with, the hydrology side, where one of the main models we use is the community water models called CBATM on the left. It's that's the high resolution course to high resolution, multi-resolution model, global, regional coverage. It's an open source model written almost completely in Python. Everyone can download it, use it, modify it. It's distributed via GitHub, but we also have kind of support that we can kind of community that support itself, but we can also provide support with what people modeling with it. That has multiple inputs, but the outputs are mainly kind of hydrology and water driven outputs that can go into other models. So Marina model is for kind of nutrients transfer. It's not for IIASA, but or not for our group. But we also use it sometimes to include water quality issues with it. So then you get hydrology, water demand, and some nutrient concentration. And put it all together into ECO. So ECO is hydroeconomic model, of the group, and then we can come with this identifying the least combination of solution options. So what type of management will be economically most efficient in different settings, under climate change or under different socioeconomic pressures, etc. One thing that we are currently developing, and trajectory development is 1 to 2 years. We start this January. Is this CBATM water quality, so WW2, so placing a bit in use of Marina, but getting nitrogen, phosphorus with flows and expression within the hydrological model, and soil erosion, sediment delivery into streams, into reservoirs. This is currently kind of in the process of development, and I think the phosphorus sediment model should be already occurred in the end of this year. Not this year, but next year. This is where we are going with the CBATM. Some kind of example, very minor, like the users that we have for users that we have, and the application of CBATM, starting from this CBATM that has all these processes on the right top, all these processes that are partly human-driven, like pumping water, building reservoirs, or natural, including precipitation, runoff, infiltration into the soil. And this is the hydrological side. Then we can have different applications of them on different resolutions. So the quarter resolution that we use is about half degree, more or less 50 to 60 kilometers on the equator. And this is a global discharge. It's a calibrated model, global model at 60 kilometers. Modeling discharge. This is the time series that we're trying to show. Of course, just for the Israeli case, it's irrelevant this resolution. And then we go further to more relevant resolution for the Lake Victoria Basin in Africa. We have a already set up model for 10 kilometer resolution, possible multiple countries. For the Dima Basin in India, which is quite a huge level 1 model, 1 kilometer model calibrated. I will also show some of one of the applications we did for Israel for the Eran Basin in Israel. In the later slides, the resolution goes from half degree, the course of then to 30 seconds. It's about 1 kilometer at the equator. And as I mentioned, it's open source and modular, so you can also develop your own modules, your own capacities. You see them, you know, Python, and it's I can also acquire quite easily. Yeah, it uses a daily time step simulation. Let's see what happens. Another development for CBM is the integration of groundwater processes, a bit more complex groundwater representativeness in CBM is using ModFlow 6. So ModFlow is a USGS model, also easy access. And what one of our colleagues decided below was done is basically couple these two models or divide simultaneously turn by turn set information. So you can run CBM for almost surface hydrological process. And CBM has its own groundwater representation, which is very basic. To get it a bit more complex, we use ModFlow. So water from surface penetrate the soil, infiltrate the soil, penetrate different soils, and then get groundwater recharge, and then ModFlow take it and calculate all the lateral flows and the heads that we say water tables, and calculate base flow capillarize, which goes there to see the depth. So the two models linked together, and you can have a bit more complex representativeness of the groundwater processes. This can be also run at a high resolution, so like 500 meters, 200 meters, 100 meters also have applications. Just depends on computing power that you have. So this is some example from implementation of ModFlow. It uses the Dima Basin in India. All of these points are boreholes to monitor levels. This is the over time average water table depth. This is the measured one. This will be the simulated one from the model. You can see that if you just consider the correlation, the performance is not that well. We have some points that kind of cross the line. We have a lot of over and underestimates the model. But if you look at this time trend, so if you take not specific bore, but you just try to get the region as a whole, and you get the average, look at the trend of the time. So if you look at the time frame, you see this model doing this quite well. If you get this dynamics of the table, but this specific location you is represented. This can be caused by many things, including the scale of the model. So boys at the escape point in space, but we model it at 500 meters. So it can be quite a lot local conditions. Another development is ongoing for ModFlow is that we usually what we have now in ModFlow is just like this one layer of aquifer. This is representation of this of the Mamane aquifer here in Israel. This would be like cutting off around Ayalon, the Aviv area. This is the Mediterranean Sea. This goes towards these Judea mountains. And what we have put in ModFlow is one layer, so one aquifer, one layer of aquifer. This stands for the aquifer. But actually, ModFlow has higher capabilities. You can have multiple layers, and this is what we are now embedding in CBM. This is how we do it for Israel. So we have this coastal aquifer, which is this kind of bucket, but then we have aquifers, so it's relatively shallow. And then the mountain aquifer, which is quite deep, so it has this phreatic zone where breaching actually occurs, and then the water goes like this way beneath an aquifer, I would say, a seed there in the Shvela and the lowlands. So with this layer approach, we can actually model this more realistic representation of the aquifer and allow vertical changes in hydraulic properties. And we also apply this fusion, it's still in development, but we applied it to the Sab aquifer in Saudi Arabia and Jordan. It's quite a huge aquifer, which is all confined. So it has this sealed layer and fossil water beneath it. So it's barely recharged. It's just ancient water that is stuck on the ground and they use it. And they wanted to see the potential of how many years they can actually be using. So we apply this model with the layers. This is the layer on top, which is sealing one, and this is the actual aquifer. And here and it's also a bit cycling, but to calibrate Saudi Arabia was quite challenging because discharge in rivers, which we usually use to calibrate, is not there. Due to its very high aridity part there. So we use actually a GRACE, which is a satellite product of total water storage in an area. It's gravity approach based. You get the trend of how much water, the changes in water storage, total storage of water in soil, in groundwater, in reservoirs over time. So this is what we use to calibrate, and this is the results again. So this would be like silicon is the red line, and the blue line is GRACE trend, and you can see basically that GRACE is a bit more spiky, but more or less this also the seasonal trends and the decreasing trend is captured quite nicely. But what we basically see here is that a lot of water are being extracted from the region. So this is reduced in storage over time. And this storage is mostly coming from this aquifer. So they're basically pumping the water out and reducing the storage of water. And with this coupling, you can also say a bit about how many years they can proceed with doing so. So this is just the correlation, which is better than what we saw before. So to another field or approach is to couple hydrological modeling with agent-based modeling. So just in brief word, agent-based take different actors, agents in a setting. It can be farmers in this one and government agents. And each of them is individually making decisions about their kind of management of their farms or the policies that they advance. So this one takes UATM, and the GEP is this agent-based modeling that we developed by Jens, which is also cited below, and this is the GitHub for the model. It's also open source. And the inputs are storylines, so different policies that you can, different policies that can happen that are reasonable. And the agent-based part is the different agents. So over 1 million, almost 1 million farmers in this one, in the Diva basin in India that they model, and some also NGOs, participators, NGOs that work there, and the government agencies, so basically regulation. And then there is the interaction between the hydrological model and the agent-based model. So the interaction here is the farmers decide based on their interaction with government policies, with NGOs, how much water they would like to extract and what crops they choose under different scenarios. And then they send the water demand to see what happens, which extract the water, figure out the hydrological implications of this extraction, and send back information to the farmers. This extra information allows the model to run. And of course, different scenarios can be like climate change scenarios and other socioeconomic scenarios. So in this result, this is like just a proof of concept that the model works, and then working now on the actual case study is collecting some data on the actual agents in the Bioma basin. But this is, for example, groundwater irrigation from in this area in the River Basin. These blue points, all the blue points are agents. These are all farmers, different farmers that use groundwater for their irrigation, and their decisions based on different scenarios show the reduction in groundwater levels. So what you see is basically groundwater table, water table drops, the pumping out groundwater based on different scenarios. So for example, this NGO adaptations, this one results in the most kind of modest reduced reduction in water table. Basically, in this scenario, NGOs spread this storyline is the NGOs spread some knowledge about how to reach 80% of water efficiency, irrigation efficiency. And this is for a kind of a small group of farmers, and they have their social networks, and there's some probability that they will spread it to their neighbor farms on a daily scale. And over time, this proves out to be the most efficient way. Of course, this is like a made up data, but then if you go out, and this is what I'm doing now, collecting data for farmers, you see farmers there, collecting data of NGOs actually working there and governing policies, then you see the model is actual data. This is the next figure for this model. Another tool that we have together with PAU, okay. The food World Food and Agricultural Organization is this global and agroecological zones. It's found originally started with FAO, and then IIASA joined in at early development. So guys, Fusion 4 is out, and this is quite a nice data set about the biophysical suitability of over 50 crops. I think it's now at 10 kilometers with 5 arc minutes resolution. And this is modeled by more than 300 generic production systems, has the historic and current and future trajectories and different scenarios of representative greenhouse gas concentration pathways for 3 periods, I think it's 2020, 2040, 2080, I mean, these 3 future periods averaged out. And what you can see throughout the example, just showing how it looks like. So you have this, for example, grain-fed. I think this is wheat, potentially grain-fed wheat, between 1981 to 2010. It's historic data. And then I just choose one, for example, just one global circulation model. So it's one data set for future precipitation, future climate, and under specific concentration of greenhouse gas emission in the atmosphere, and also check the rainfall positions. So I visually just to show the different, I put out in circles the regions that yields are lost. You can see Ukraine and Russia, which is in better days are one of the top producers of wheat around the world. You can see France also using quite a lot of wheat in the middle of wheat, which is also a big producer of wheat globally. So this is just to show this the data, but I encourage you to go to the link here and see the data. I think this is part of your research, is quite easily accessible and massive database. I need to hurry up with the 5 minutes plus 5 minutes, so 10 minutes. Some research that we are doing now is this one water methodology. So this is an indicator suite developed, supported by the World Bank, applied for Eastern Europe, Eastern Central Europe. And the idea is to develop a methodological framework for assessing quite fast water security and come up with an action plan of increasing water security in different countries. It takes on 4 different dimensions of water system endowment, so basically how much water do we have in the system, what are the demands. Architecture is the institutional capacity to manage the water and the infrastructure out there, so irrigation system, dams, hydroelectricity. The performance would be mostly about water management, what policies are in place, for example, to manage the water, to manage the resource, and the outcomes, so what all of these actually mean for economic, environmental, and the social dimensions of people living there. Currently, we are doing our second batch of case studies. We have deep dive countries. We already done Serbia and Croatia, now working with Montenegro, Bosnia and Herzegovina, and Albania. And then we go for kind of regional assessment as well. These are all these long steps of this methodology. The other step, of course, that this is like diagnosis and narrative making, but then we actually come with action plans, which is also involving interview of stakeholders and workshop with stakeholders in the policy arena in the countries. Yeah. GATWIP is this global assessment of treated wastewater irrigation potential, something that I work on personally, and we take like different technological scenarios, and starting with the idea is to basically to assess how much irrigation can we achieve with treated wastewater globally. So Israel is quite cutting edge with using treated wastewater for irrigation, but otherwise in other places it's not that developed. And we try to come up with the potential. So the question is, what is the share of water irrigation requirements is can be satisfied can be satisfied with water with treated wastewater. So these different scenarios start with the baseline. We just take currently treated wastewater, especially and allocate them for irrigation, either on the same place that they were, same grid scale that they were originate, or we try to convey them, move them around up to 150 kilometers. This is the sensitivity which is, and then we go up with trying to either improving treatment quality, so we don't have a restriction on irrigation, or we take all collected wastewater, or then at the long term all the generated wastewater globally, and we say, okay, we now can use them for irrigation. What is the potential? So it's kind of theoretical exercise, and these are some initial results. So we have this, we can allow irrigation either under only in water stressed regions, so where you actually has high competition for the resource, or also at all places. And this is, so the number is, this is around 12%. This is 12% from irrigation requirements that can be satisfied with treated wastewater. And if you go only for water stressed regions, so it's around a little bit less than 6%, maybe 5.3, which is also quite a lot if you consider water stressed region and their problem with getting water. And this is just an example for the effects of water conveyance. So if we can move water around, this is Beijing here, this is China, and so the red areas around Beijing, these are areas that are benefiting from increased satisfaction of their water requirements just by if we move the water around. So this is moving water around 40 kilometers relative to this 0 kilometer or 5 kilometer alternative. Just a bit about the Nexus approach, something we do. So in IIASA work with different groups, and we can also collaborate within the organization. So about the first field project, basically the first field project to come up with this, and this is like multiple groups in IIASA. It's not only the water team. It's so the idea is to come up with a framework that kind of mainstreaming crop production cycle, basically taking stakeholders from one side, the social discourse from one side, and then scientific modeling approach from the other side, putting them together and apply them for a real world problem. This is the focus here is in distributional justice and how it can support risk management in nexus issues, combining in this case ecosystem services and conservation of forests and versus managed forests, and the hydrology, of course, the justice in the population. So we have again Sibaden with GAP. Now GAP, instead of being farmers, it's land managers, so they decide on which type of forest, how to manage the forest. And this is coupled with plant fate, it's an ecological simulation, another agent-based one, simulating forest, trees growth in a forest, and community structure. This is from BC group in IIASA. And then final output will also be the application ecosystem services, and how these forest environments or different trajectories of knowledge serve the populations, and of course, this goes back then to distributional justice of different densities. Yeah, so finish with slides. Winter Israel's flexibility for Israel. What we've done here is mainly a development to allow basically Sivotem to be applied to Israel. So we focused on Ayalon, the orange one, and Sorek, the blue one. But in order to make Sivotem relevant for Israel, we had to do two major developments. One is this wastewater model, basically take water from consumption or sewage and put it into wastewater treatment plants, two types here. And then it can be either reused for reservoirs to water consumption against irrigation this time, or discharge in rivers or to the sea. And the other one was this interbasin transfer model. So we basically, this is an initial attempt to do basic distribution network. So Israel is a place that runs nationally. It's not a basin scale management, but national management. And we need to move water around in order to actually simulate what happens here and actually go national. So this would be the national model if it will happen. If we decide to go for it, would cover this basins, something within Israel, something contributing from other countries' water into Israel. This is some results. I'm actually not going to cover it due to time. Also, this one, some upcoming project. So yeah, that's what is just to show. Basically, it's quite a big project with the EU Horizon, big foundation with a consortium of 11 partners, basically dealing with localizing this concept of boundaries, global boundaries, planetary boundaries of resource extraction, resource use. So and water use is one of them, and then is to kind of regionalize and localize the boundary for water use. So this is what we're going to do here. Swap Uganda is the water quality model that for Uganda kind of covered. And just this is an important slide, so maybe 2 minutes of this and I'll finish. So opportunities to collaboration. So we have different ideas of how we can collaborate, but we have this water team here and collaborating within IIASA with other IIASA groups. And then you have different research institutes, academic Israel, with researchers and students linked to other, of course, institutions, and then also to government agencies. I think I put it in purpose because like the collaboration, I think, with Israeli policymakers would fit best actually through an Israeli partner from academia. It can better collaborate with these local policymakers. This is the policy side of also important side of IIASA research. And then what comes into mind first is like this joint research proposal. We have our resource funding and partners, you have yours, bring them together and let's work together to come up with research proposal. And this is more this kind of formal researchers approach. But on top of this, we have also this knowledge exchange and capacity building. So we can propose research stays, like we can, in research day, we can provide the office and the time from our scientists to supervise or to discuss ideas. And the YCSP program, I will give it one slide. Postdocs, which is currently we don't have open positions, but we still need to figure out if IIASA Israel postdoc is continuing at the one public. And yeah, and tools and support. So the models are, you can access the models, you can use them, we can also provide some support by using the models. And the YSSP is this Young Scientist Summer Program, happens every year. This is an NMO. This is basically the member state funds the stay of a PhD candidate or students, a 3-month stay during the summer within one of IIASA's research group, and then you get the supervision to do your summer project. Usually it ends up with a quite nice publication as well. Contributing both to the group and then also to the PhD of the student themselves. Applicants should connect in advance the desired group. So do a bit research, go to the website, find the group you are interested in, and connect the group to develop the project proposal. So it should kind of co-benefit the PhD student and the group. And then we, as the water security research group, encourage you basically and Israeli candidates to apply, and this is the deadline. Still, you can still apply in January. This is the link here. You're not available to push it. Okay, I think this is for me. Thank you. It's a bit over time. Sorry. If you have very few questions, I can answer some, but also a lot of information.
John, I want to go to the next talk.
Yeah.
I just want to make a few comments because lots of students.
Yes.
I'm glad you ended. Sorry, I'm Gary Pillay. I'm retired. I'm a molecular microbiologist, but I worked in the council of IIASA for 400 years in the vice chair of council the last 6 years. So they required assistance here. So I'm there for about 7 months. But I'm very interested, and I work very close with Israel. I'm bringing them as a member in 2017. And then I work with IIASA and Eran now for the new findings. So the budget, etc., that you refer to is all built in there. But I think what's important is that, as you pointed out, the big money is not about the budget from Israel or it's about the joint proposals that are made by Israeli researchers and NASA researchers to the Horizon programs, for example. That's what the big money is. I mean, at the moment, there are proposals from Israeli and NASA researchers which worth 12.1 million euros. We don't know what the outcome of that would be, but that would be the big money. The other thing was very disappointing, as I said to Itai, it cannot be business as usual. You need to step up again with the number of postdocs, the number of YSSP. Last year was not a single application from Israel for the YSSP program. Yet there are many eligible students here. They've given an undertaking that they will fund up to 2 YSSPs for January, for next year. So I think they encourage you to apply. If amongst the Israeli university, you want an online kind of a workshop on how to apply, that can be arranged, and you can do that through Fabian Bond. Okay. The other thing that you can do is say, take seawater in as a model, and you want to teach the students about how to use a model, etc. Then that can be arranged. You can have an online course on the use of models.
Yeah.
Then there's the use of, for example, how to publish in Nature. You can have an online course on that, so that students can then, visualize what their research is, what to look for, etc. So I think, and I'm saying this to you now because there's lots of students here, you will only get as much as you want out of IIASA.
It's also for the faculty, not only the students.
For everyone, yes, for everyone, for everyone. There's emerging researchers, there's established researchers. The established researchers, of course, there's short to long-term stays from 3 months up to 12 months, okay? It can be 24 months. But I'm just mentioning this here because no place I go to, it's not because of a lack of application, it's a lack of not having the information, not having the links, etc. So you've got time to apply for the YSSP, but you also have time to apply for postdocs, etc. And I think the arrangement is that because there's going to be a knowledge center for system analysis in Israel, that's going to be the interface. It's going to be like a hub and spoke model. So I think IIASA is one of the spokes, if you think about Israel being the hub. So I think there's some exciting stuff coming in, but you'll have to keep your head close to the ground, so to speak.
We also already had like one workshop in Israel in April. That's for 2 days workshop in Haifa, and to different scholars. Eran posted us, was very nice. And I think we can definitely do another one. Online is very easy, right?
I will be going to Technion tomorrow.
Yeah.
And then I will speak to the students there and then such.
Yeah.
And I'm going to invite some this afternoon.
What would be good is to have some seed money for joint workshops.
The workshop you don't have to pay.
No, to have workshops from there to have idea on a workshop, and then to have this idea to work on it so we can apply together for Horizon.
That's really great. So what's going to happen is that when this knowledge center is announced, I think the Israeli government will put 3 million shekels, and the host has to pay 1 million shekels.
Yeah.
But the whole idea is to have a fully fledged, comprehensive human capital development plan to train the next generation of researchers from Israel in system analysis.
Yeah.
And I think that's where you need a central point where everyone
That's fair.
others are being interested. But I just thought I'd share it before I run to the other place.
Thanks for joining.
Thank you. Thank you, Doc. And by the way, the water model you work on, Korea is also working on it, Vietnam is working on it, so there's multiple countries. So it's not just.
Okay. everyone speaks Hebrew now? נדבר באנגלית גם? האמת שאנחנו גם מפונקים. Okay, so we're also recording, stay with English. Forgot. Okay. אז Hadas?
Yeah.
אפשר אולי לדבר על יותר רע, כי לא כולם...
כן. בדרך כלל אני אומר שתהיו לדבר מהר.
Okay, so hi everyone. I'd like to talk about treatment of sewage ponds in rural India. Okay. So the question is, we all know that water is life, right? So what is sewage then? And when I'm asking that, sewage is mostly water and only a very small percentage of contaminants. One of the issues that one of the active issues in the world is that 88% of diarrhea associated deaths are attributed to unsafe water. It's mostly contaminated by sewage and insufficient hygiene. Diarrhea impacts child growth, and one of the main causes is rotavirus. And these germs are usually spread through contaminated water, foods, and objects. And sewage is the main reason for contamination of the water sources. The EU has set a goal of achieving zero pollution for a non-toxic environment by 2050. So how can we reach this tremendous goal of having a non-toxic environment? If we look at conventional wastewater treatment plants, and this falls into what we were talking about, they're highly efficient in treating the sewage and removing organic matter, nutrients. However, they are unfit for low and middle income countries and many, especially in rural areas. And they should, by the way, I think, integrated also to the model, not only the places where sewage is collected and treated. So 360 kilometers cubic meter of wastewater is produced per year. Only 10% is treated in wastewater treatment plants and reused. So this means that all the rest is either not treated or treated and discharged to the environment without being reused. And in addition to that, water is not disinfected. So therefore, disinfection of water is the last barrier prior to consumption of water. In addition to that, the climate crisis is forcing farmers to grow food in sewage water. Many farms in countries around the world actually do not have any other choice rather than using raw sewage for irrigation. And this actually is much more than anticipated in many countries in the world. So what can we do about it? I'd like to share a project that we're doing in India, looking at sewage ponds. So what is a sewage pond? A sewage pond is actually a pond of sewage. The sewage is discharged from the households into a central location without any liner in the groundwater. Therefore, we have infiltration of the sewage to the groundwater sources. There's no treatment of the sewage. We have algae growth, plant growth, waste, and whatever. And these ponds actually then are used for agriculture irrigation. These ponds can be small or large. The depth of the ponds could be between 1 meter to about 3 meters. And with no treatment or incidental treatment. And therefore they actually are an environmental hazard. And they result in many health problems in addition to soil damage. So our goal is to scale down, is to localize sewage treatment in rural and urban areas with economic benefits, but mimicking nature. So in nature, there's a process where algae and bacteria can actually join together to improve the sewage quality. However, since it's incidental, we want to actually engineer the natural processes in a low-cost way without any retrofit of the sewage ponds, because the farmers, they do not have the capacity or the capability to actually build a treatment plant. And therefore, we use this process. In addition to that, if I'll have time, I'll also talk a little bit about the barrier to pathogens in our drinking water. So this is the joint work. In the center, we see a Sichuan, he's a guru in North India, and actually he has a movement of cleaning the nalas, the streets, and all the areas from sewage and waste related. So what is the concept basically? These are actually sponges. So sponges like when we take a shower. Whenever we have a surface in water, we have microbes attaching to the surface. It's like in the morning while we brush our teeth, is because we have a layer of microbes that actually are attaching to our teeth and we brush them. So basically the bacteria and the algae, they attach to these, the bacteria and the algae, they attach to these sponges and they form a consortium where the bacteria can take the organic matter from the sewage, discharge and resolve in formation of carbon dioxide, okay, which the algae take and release oxygen. So this is actually a small factory that generates oxygen in situ into the sewage treatment plants, and therefore we can actually purify sewage using a nature-based solution without adding oxygen to the sewage. And I would like to share a little bit results of things that we're doing. Otherwise, jumping. Okay. This is a paper that we published on how these processes actually can remove micropollutants from our sewage. So you know that most of the drugs that we consume actually are dumped to the sewage. For example, if we take an antibiotic, 90% of the antibiotics that we take are dumped into the urine, into the sewage, which are also an issue when we think about agriculture irrigation with especially with non-treated sewage. So what we show here is that this consortium of bacteria and algae were able to remove, for example, different micropollutants like venlafaxine and carbamazepine, which is an epileptic drug, using this simple treatment. We are actually designing an entire process where we're taking the sewage ponds, removing the big solids, removing everything that floats. We also develop low-cost sensors that allow us to measure the health of those sewage ponds. In addition to that, we add into the sewage ponds these supports. The water is used for agriculture irrigation, and also once once in a while, we collect these supports which float on the water. We remove the biofilm from them in order to produce a biofuel, or actually to extract the phosphorus that is embedded within the biofilms. However, sponges are made from plastics, and plastics are made from fuel. So this is actually not a very sustainable way to go. So we kind of thought what we can do differently. So we thought, okay, let's develop the mushroom. The mushroom actually mimics a mushroom where the cap has air, so it floats on top of the sewage ponds, and the leg is actually a huge surface area where the microbe and the bacteria can attach. So this is how these actually carriers, this is how they work. They float on the water, and they are an area, they provide surface air for the microbes and the algae to attach. We also did a small pilot study with 7 cubic meter of sewage, and now we're doing a big pilot study that we don't have yet the results, but we'll have them soon in a few months. And here we can see, for example, degradation of the organic matter in sewage pond using this technology. And we also used the water post-treatment to grow weeds. And we're also checking the health of the soil, the health of the water with a control study. And the next treatment, the next stage is to go to large-scale treatment. However, all these treatment technologies will not work if they are not adopted by the local people. Therefore, we're combining both society, technology, and economic aspect within the treatment, and we're collaborating with different researchers from different fields to find a way to actually treat those sewage ponds. So will the farmers use this technology? We did a huge study that we're now analyzing the results in the Punjab area. And what we saw is that some of the farmers actually use groundwater, others use wastewater, others actually irrigate the crop with mixed water. It could be sometimes groundwater, sometimes wastewater. The wastewater can be raw or someone treated. So there are many different scenarios, and the only way to understand what the farmers are doing is actually to go to village by village, and we developed a survey trying to really understand what's happening and what are the farmers doing within their crops, with different types of crops, by the way, and also different time zones within the crop. So this is some of the students that are in the field, and we wanted to assess the water quality that they're using and the soil quality. So just like a very quick example, what we saw, for example, is that in areas where farmers are using sewage ponds, they actually have less tubules in their plots, which makes sense because if they are using sewage, they need less groundwater. And in light of the issues with groundwater scarcity in Punjab area, definitely this we need to actually look at sewage in a different way, because due to the climate crisis, farmers have less water to irrigate, and therefore they use water that is marginal in its quality. We also wanted to know, will the public consume food that was actually irrigated with sewage, treated sewage, okay? So we went to the markets and we developed this survey and questionnaire where we told the people that were purchasing the food that part of the food is irrigated with groundwater, the other one is irrigated with treated sewage. Then we also looked at a reduced price. So would price be a way to incentivize the stakeholder, which is actually the public? Will they eat crop that was actually irrigated with treated sewage if the cost is lower than food that was irrigated with groundwater? And what we found is that when we reduce the cost of the food, we can see that actually more people are willing to purchase food that was irrigated with treated wastewater, because it's not enough to use the technology to irrigate with that food. We want to understand, will the public accept this as a food source? And we asked why groundwater. Well, 30% thought it's healthier. We asked why treated sewage. Well, we were actually very happy to know that 20% of the people actually thought that treated sewage is a more sustainable source for irrigation. And this is a very positive point, because we can build on that, also look at more at education. So it's not only the models or the mapping or the water quality or the soil quality or all these things, it's also, will the people use these technologies? Will they adopt them? And what do they think about this at the end? Do you have 4 more minutes? Okay, good. So I'd like to shift to a different project that we're working on. So assume that the water is contaminated, the drinking water is contaminated with sewage, and we don't have any treatment. And what we found is that in many places that we analyze the water quality in rural areas, the water is contaminated with microorganisms and also heavy metals and various parameters which actually limit these water as being safe. We developed a technology that is funded by the Asaf Foundation. It's a Clean Water Fund for developing decentralized treatment solutions in rural areas around the world. We're working in India, in Africa. We're starting a project with the Palestinian Authority and maybe also with Jordan, trying to see what we can do to support clean water also for irrigation, but also for drinking water. One of the things is that even if we treat the water, the sewage for agriculture irrigation, there's still a possibility that this effluent, even if it's treated, will have a high concentration of fecal coliforms. And these fecal coliforms are actually, we're actually limited in the concentration of fecal coliforms that we can use for agriculture irrigation. Different countries have different regulations and standards. However, the only way to reach safe water for food crops is by disinfecting the water, especially in decentralized treatment plants. The treatment is usually at a lower quality compared to large infrastructures and wastewater treatment plants. Therefore, we really need to emphasize the disinfection of these water. So what happens in rural areas? Boiling is unscalable. And also in addition to that, we did a study that also Asaf was involved in Kerala in India, where we found that even post-boiling, the water still had coliform because the people, they had intermittent water supply and intermittent electricity supply, which means that they had drinking water every 3 to 5 days. So they had to actually boil the water and keep it in storage containers for a few days. Water, when it's stored, if it doesn't have any residual disinfection, or if the storage tank is dirty, or if they put their hands inside the water, or for many, many reasons, it gets recontaminated. And we found that even post-boiling, it depends on how we boil. Do you boil for 1 minute, 2 minutes, 3 minutes? So everything impacts the water quality. Chlorine is not relevant for remote areas, desert areas, infrastructure limit areas, because there's no supply of chemicals. And filters, they require pressure and energy, which is also a problem. Therefore, we developed a technology which is upgraded bio LED-based technology that can fit rural areas. It can actually be in the size of a cup or in the size of a laptop. It'd be connected to a water pipe, or actually the LEDs could be powered just by the flow of the water. So it's really intermittent in many ways. However, LEDs, they have tons of advantages. And if we look at the Corona crisis, everyone wanted to disinfect everything. LEDs have a quick startup time, so it's just like turning the light on and off. They emit light, and this light actually kills the microorganisms. However, and they're also mercury-free. However, they're costly, they have high energy consumption, and also in addition to that, there is issue of recovery of microorganisms. We developed a patent that can look at all these different elements and actually result in low energy consumption, low recovery and regrowth of microorganisms and biofilms, and also the system can also be connected with an IoT that ensures continuous operation and effective maintenance. We're now planning a few pilots in different locations that also looks at the disinfection, but also at the storage tanks. I don't have time to talk about it, but we're developing a blue light-based technology for storage tanks. We won several awards with this technology, and I'd like to end with, this is one of my students actually invented lidded gear. And that's it. And our lab journey is to actually save lives and save water. Thank you very much.
Thank you, Hadas. Are there any questions? So we'll go next is Asaf. Shall we order the next people plan? Yeah. But also something in the chat. Just from
Okay, so everyone, I'm Asaf, PhD, the common mistake. A PhD student at the Hadas lab and the Water Tech lab. And I present today one of our works about the nowcasting with the fecal coliforms presence using an artificial neural network in India. So the motivation is, as I hope you all know, about 2 billion people around the globe lack safely managed drinking water. Of them, more than 700 million people are lacking basic drinking water services. And from those, more than 150 million people are drinking directly from surface water, as you can see here picture, in this case, a photo from Tanzania, but in many places around the world. And on top of that, millions, tens of millions of people are drinking directly from groundwater, again, directly without any treatment before drinking the water. And all of this is leading to the terrible number of about one child under the age of 5 that dies every 2 minutes, around the globe again. Now, as you all know, because of the population expansion, which is keeping going higher and higher, we just crossed the 8 billion people, and this will get only worse in the urbanization and the industrialization of this. All of this is leading that we will have more effluent pollution, and when you combine this together with places that have insufficient sewage infrastructure and are lacking with water treatment plants, we are resulting with contaminated water sources. Again, this is not happening only in places as developing countries. It's also happening in the modern, what we call the modern world, the developed countries. You can see this happening across the United States, even in some places in Europe. And obviously the way that the authorities are trying to make sure the water is actually drinkable, safe to drink, is about quality, water quality monitoring. And in most of the parameters today, they're able to do it in real time, in situ even, including physical and chemical parameters. And obviously the biological contamination, which leads to most of the health issues, obviously including death, is an integral part of the water management. Now, the problem with the way that we're still today monitoring the water, the biological aspect of the water, is that we're still using the traditional method of counting CFUs, coliform colonies, or using the MPN method, most probable number. By the WH standard, obviously, for drinking water, there should be no biological contamination. Again, fecal coliform or E. coli. And this traditional method takes between 18 to 24 hours to get the result. And it's not including the fact that you need to take the sample, take it to the lab, and again, wait all this time. This leads to, in most of the places, the water is biologically tested about once in a week or once in 2 weeks. And when you go to the rural communities, it gets up to 6 months between each water sampling. And this is something you can also see in Israel. Just I think it was last week. You can, don't know if you saw that, but on the websites, Mekorot announced that in some places in the north region of Israel, in the Galil Elyon, the water is contaminated, and you should boil the water for drinking. Now, obviously, this is a good idea to boil it if it's contaminated, but no one really knows how long it was contaminated before they announce it. Just because, again, the routine is not checking every day, and obviously not even every hour. And contamination is something that can happen really fast and really quick. So our goal was to find a cheap, real-time in situ, probably, a solution to monitor the fecal coliform problem. And we were able to obtain data, in this case, from India, also India, as you can see, this is some of the data on the right side, from a variety kinds of water sources, including surface water and groundwater, with a large number of parameters. And our solution was using, again, building a fecal coliform sensor using the machine learning or AI algorithm, which again will use easy to monitor real-time in situ parameters that can be implemented in the field. And in this way, we can now cast the fecal coliform absence or presence and shed light on this gap of time where no one knows what's happening in the water today. And so the method that we came up with is using a multi-layer perception model, AI algorithm, which takes, as you can see here, the water quality parameters that again can be monitored in real time, such as temperature, pH, conductivity, and so on, alongside with some geographical parameters, including the type of the source, again, if it's a lake, if it's a river or groundwater, and some parameters about the location. Now, some of you might ask what is going on here, because there's no correlation between the temperature and the presence or absence of the fecal coliform, and obviously for each one of those parameters. But when you look deeper into the data, you can see that there are some correlations when you cross more than one parameter. And this is what the AI is doing better than us, finding mathematical connections between the parameters, the inputs. And we chose, in this case, to make the problem a little bit more simpler. So the output is just the presence or the absence of the fecal coliforms. Again, according to the WHO standard, which says there should be no fecal coliform in the water, for drinking water. Now, the results are based on the fact that we took the whole data, we took a chunk of it out, we trained the model, and so the test result, the test data was not shown to the model. And in this way, we can check the model, how the model acts and performs on data that wasn't shown to them before. Here you can see the metrics. The x-axis is the predicted label, what the model says, and the true label is just what the lab test showed. And in total, we see that the accuracy of, again, finding the true times where it's absent and true times where it's present, more than 92% of the time it's right. Even more important, the sensitivity, more than 98% of the time it's right. The sensitivity is about how many times the model and the lab tests are saying that the water is contaminated, from all the times that the lab said it is actually contaminated. And also important, the precision, obviously, maybe I'll show it, yeah, okay. So I'll just recap on this one. So in this case, the true negative is actually, there's no problem with the water, people can drink from it without any treatment in this case. The prevention, the true positive, is actually when we prevent from people to drink and address it as they should treat the water. The false positive is where the model says that the water is contaminated, but from the lab test we saw that it's not. And this is what we call a false alarm. The worst case, obviously, is when the model says that the water is good to drink, but the lab tests show that it is contaminated. And obviously, we wanted to minimize the false negative, the worst case scenario, and it results in these numbers. Last one is the specificity. This is actually just like speaking about the sensitivity, just about the samples that were not contaminated according to the lab test. When you look deeper into the results, we wanted to see how good the model is predicting, obviously about, again, presence of the fecal coliforms, but if it has any relation to the biological load, okay, how much MPN was shown in the lab test. And we divided here according to some ranges. You can see on the y-axis the ranges. In the brackets, you can see the number of the tests that were in that range. And obviously the x-axis is the accuracy in percentages. So we can see that, first of all, that as the MPN is going higher, the fecal coliform load is going higher, we are showing better accuracies, and this is great. We can see also that in the range of what is called by the WHO a low risk range category, we're predicting with lower accuracies, but still about more than 81% of accuracy, which was nice to see. Again, this is the range which is slightly contaminated. Obviously, it's not good for drinking water according to WHO, but again, it means that the water is having a low risk about health issues. Another thing that we wanted to see and to check is how certain the model is when it says the water is present or absent about the presence of the fecal perform. So here we can see the probabilities for each sample. On the y-axis, you can see the number, the percentage of the sample for each group. In green, the absent group, and in red is the present. When you sum up all the red columns, you will get 100%, and accordingly to the green one. And you can see here that in both cases, also the present and the absence. In most cases, the model is 100% sure that the samples are contaminated, again, in cases that they should be contaminated, and absent when they should be absent. Obviously, we have here some the dash line I didn't spoke about, but this is the threshold. Everything that is higher than this dash line, the model classifies as present, and below it it's absent. So we can see here again that in most cases the model is definitely sure about its prediction, and specifically about the present, it's more it's giving higher results, just as we saw in the confusion matrix. From this, we can see that there is some trade-off that we can do. We want to look at the different scenarios that we just spoke about. The precision, where we want to allow, let's say like this, less cases of what we call false alarm. So we can raise the cutoff, the threshold, to 0.75. And in this case, the accuracy and sensitivity will go down a little bit, but we will gain higher precision and specificity. And in the same case, we can take the cutoff down to 0.25. And we'll see that the accuracy is keeping a bit the same, slightly higher, but the sensitivity is standing at almost 100%, meaning that in most cases, we're able to prevent from drinking contaminated water. Obviously, here we pay in the precision and specificity. You can see here that the number of the false positives is getting higher. So in summary, maybe just these are the numbers that I just talked about. In the general model, we see that we're getting more than 93% accuracy, sensitivity of more than 98, and precision of, again, 93. We can play with the trade-off between the precision and the sensitivity. In this picture, you can see that we're taking this model, not only keeping it into, on the computer, we're taking it into the field. We're building the sensor so we can test it. Also in India, we're also planning to have some field trials here in Israel. And that's it. Thanks for listening.
It's very interesting talk. If you have any question for Asaf, we have time for one question. Suppose will leave us at 12. So not just straight to Eran, we bit about the different things from the last two talks. Just manage. Whatever.
Okay, so right, so I'm Friedler. I'm from the Department of Environmental, Water, and Agricultural Engineering at Technion, and I'm currently the head of the Groundwater Research Institute. And I'll talk about modeling and monitoring urban and rural water systems. And the question, can it support decision making? And I'll give a short introduction about the Water Research Institute, and then I'll show three examples.
Sometimes it works, sometimes it's not.
Right, so the Nancy and Stephen Grand Water Research Institute was established in 1993 in Technion. Is a Technion-wide research institute. Its mission is to be a center of excellence of international caliber and the leading water research institute in Israel. Research in science, technology, engineering, and management of water. It focuses mainly on topics of topics relevant and important to Israel and the region, and it promotes regional and international cooperation. About 60 researchers from different faculties in the Technion, and some researchers also from other institutes. So I think that there is good grounds for collaboration between the Water Research Institute and IIASA, and the main topics are water treatment, desalination, wastewater treatment and reuse, water resources management, preservation of water quality and quantity, management, water management, wastewater management, so on, hydrology, water and environmental microbiology, urban water, wastewater, drainage system, and so on, precision agriculture, advanced irrigation and fertigation, also modeling and system analysis. So I think you know this slide. And we have funding from there's all other institutes. Basically, the institute supports the individual researchers, gives a framework for writing proposals, especially large proposals with many participants. So from here, I'll go and give 3 examples of what I do personally. And this is basically science that has to do also with decision making. So the first one will be a project called CLUA, Closing the Urban Water Loop. Second one will be quantification of lake residence time. And the third one will be on wastewater surveillance of SARS-CoV-2 for COVID-19 outbreak management. So I'll just go briefly on each of them, won't go into details. And if you want, you can ask me. Again, this project is called CLUA, but basically it's on sustainable urban water use, reuse. This is a joint project with a German colleague under the BMBF MOST funding. So we try to look on a system approach on all the water within the city, and we look at the water streams, we look at potable water, rainwater, urban drainage, and wastewater. And we look at, we take a circular approach, which means we try to import as less water into the city and to export as less water and effluent out of the city. So to have circles of use and reuse. We look at alternative water sources, but not only alternative water sources, but also looking how do they interact with existing water and wastewater urban drainage infrastructure. And we look at interactions, cross-stream interaction. What are the interactions between, like, if we collect rainwater, on what does it affect? So it affects on potable water use, and also it affects on urban drainage. And if we reuse, let's say, if we reuse gray water for garden irrigation and for toilet flushing, then it has interaction with wastewater because we have less wastewater flows. And we also judge everything according to sustainability. So we do life cycle sustainability assessment. And these are the 5 scenarios that we checked. We checked it both on Israel and Germany. So the baseline scenario is that we use potable water for all users. The second scenario is that we use potable water for potable water and rainwater, harvested rainwater for non-potable water, like toilet flushing and cleaning, laundry. The third scenario is we use potable water for water demand, for potable water users, and gray water for non-potable toilet flushing. And the third one, we use potable water and treated wastewater effluent that is pumped back from the municipal wastewater treatment for non-potable users, toilet flushing and garden irrigation and public parks. I must say that also the gray water use is also being reused for garden irrigation. And the third option is using potable water, rainwater harvesting, and gray water. And the fifth scenario is using everything. And we also have a prioritization component module that each use has a priority of a source. Like if we look at laundry, the first priority is to use harvested rainwater. If there is not enough harvested rainwater, then it uses potable water, and so on for all the sources. And this is part of the model. So the model is, I won't go into details, but it's a complex model because we have dynamic simulation, and then we have life cycle analysis on the dynamic simulation, where most life cycle analysis models are static models, but here it is non-static. And then we have optimization, where we select which source to go where. And we ran it on a model city. We call it a model city. It's a hypothetical city of 200,000 people. And the city is constructed, the Israeli city is constructed based on Ministry of Housing planning guidelines and everything. So we have a city, we have a city in the computer, we have all pipelines, potable water, drainage, sewerage, and so on. And our source of water is desalinated water. And we look at the scenarios, and the scenario where the first one is the in-house water demand of the whole city. And of course, with scenario 1, we use this is a business as usual. We supply everything by potable water. So scenario 0, in scenario 1, unlike what we thought, we cannot really supply a lot of water by rainwater harvesting due to the fact of the Israeli climate. And then we have different scenarios. And if you see with the gray water, we use the gray water, so we can supply almost 40% of the non-potable water within houses. And this reduces the amount of water you have to produce from seawater desalination, but also it reduces the size of the desalination plants. And for urban irrigation, we also get almost 50%. Treated wastewater for household is about the same, but for municipal irrigation, gardens and parks is much higher. And if we combine everything together, we can get almost 38% of the potable reduction of the potable water consumption, and then also we can supply all irrigation water by non-conventional sources. And this is the cost. We did life cycle costing, and this takes capex, capital costs, as well as operation and maintenance costs. And this is depreciated to annual cost. This is in million euros per year. And basically, we see that in all options, potable water production is the highest investment and operation and maintenance cost. Wastewater treatment plants is the second one. With rainwater harvesting, what you have is that we have investment in the rainwater harvesting systems, but we don't gain a lot. That's why it's more expensive, because we cannot really reduce the amount of potable water we use, and not the infrastructure. With the other scenarios, you can see, and this is the economic side. But if you look at the life cycle impact, you can see that we looked at electricity, and we show you 5 factors: electricity consumption, global warming, freshwater eutrophication, freshwater ecotoxicity, and human toxicity. And we can see that scenario 4 and 5 are the best according to life cycle impact assessment. Then you can combine them into a single sustainability score, which we did in a different research, where you combine and you give weights to economy, sustainability, and society. And there are methods to do it, so it's not arbitrary, but this is on a different research. So this is just giving you a hint on we make a simulation, optimization, and then do some system approach, and this can be some kind of policy support for decision makers. This is a totally different work we've done, and we've done some work for accurate quantification of lake residence time, and we use Lake Kinneret, Sea of Galilee, as a case study. And this is a true policy support. And we were asked by Israel Water Authority after the 5 years of droughts, that we have consecutive droughts, what will happen in Sea of Galilee in the future with climate change and reduction of flows, natural flows to the lake. And the minister, I'm not sure that everybody is aware, but there is already being constructed a line to bring desalinated water pipeline, to bring desalinated water to the watershed of the Sea of Galilee. And there was a question, first of all, is it worth it? And the second question was, would it be better to pump the water straight to the Sea of Galilee, or pump it north to the Hula Valley and then let some of it go back to the Sea of Galilee? And they asked us about the age of the water, how would the residence time and the age structure of the water, how would it change? So basically, we wrote a model, and actually this is currently it's an annual model, so we can assume that the lake is completely mixed. Now we're working on a monthly model that it's much more complicated, that part of the year the lake is stratified, and part of the year it's mixed, and we know we're now working out in each season where the water goes into. But basically, this model, we have water coming into the lake, and it goes into H class 1, and then during this year we pump water is leaving. Water is coming in from all sources. The sources are direct rain, direct drainage, and also water from all the rivers. The main one is the Jordan River, and the output is either pumping, local pumping, or pumping to the national water carrier, going down to the southern Jordan, and also evaporation, which is quite massive in the Sea of Galilee. So basically, we know the relative volume of each parcel of water, this year water and older water, and each parcel of water loses water to output according to its relative volume. So this is for the water goes in. Where am I? The water goes in year 1, but then part of it goes straight out with other types of water. And then when a second year comes in, so this was year 1. Now the group of year 1 becomes older. So it's now year 2. This is the bit that left last year, and this is the bit that leaves this year. And then we have another H class 1, that part of it leaves, and part of it stays in the water. So basically, at the end, we have this, we track water that entered the lake for years, and each parcel of water is being diminished in accordance to its relative volume, and the only replenishment is to the youngest age group. So this is really different from what traditional is being done in limnology. And in limnology, the way to compute the residence time is the volume of the lake divided by the inflow, or the volume of the lake divided by the outflow. And this is good when you have a steady state, but the Sea of Galilee doesn't have a steady state. So you can see the real differences with these traditional indexes, and this is not possible. The residence time cannot be 10 years in 1 year, and a year later 5. It's impossible. So, this is what we have shown. It is the mean residence time is much more stable. It has inertia, it changes with time, but also where we look at different age groups. So this is a water ample year. So you can see that the youngest age group is about 15% of all the water in the lake. But then 5 years later, you can see that it's only 0.07, 0.05, so it's 0.5%. And this year, 5 years later, is here. So we can have we track the whole age structure. So the age structure is much more sensitive. And we looked at future scenarios. So the gray one is what will happen with the average age in the lake in year 260 if we don't pump water into the lake, and the red one if we pump the water upstream and only some of it goes into the lake, and the blue one is what will happen if we pump it to the lake and from there to the watershed. So you can see a real difference in the lake residence time between less than 7 years in the scenario where we pump water to the lake to more than 10 years, and 10 years is quite a lot if we pump water, we the business as usual, and these are all the scenarios. There are different scenarios. Everything is run in Monte Carlo, so that's why you get this cloud. So and then this supported the decision to pump water into the lake. All right, so the decision was to pump water into the lake. The last 2 minutes, it's a work I've done in the Technion, COVID, and we used sewage sampling as a way to combat the outbreak and to refrain from having it widespread in the Technion. So basically, we looked at student accommodation. The capacity was about 80% full during the academics, about 4,000 students. They had to, part of their lease agreement during the epidemic, they had to report if they are positive. And we took samples twice a week from 11 manholes, and we processed it in a lab doing qPCR. Looks easy here, not very easy in reality, but we've done it. And we had from sampling to result, it was about 4 hours. And we did twice a week, 11 manholes. So, and then we compared, it's the Technion COVID committee compared, we got the results, and we compared the positive with the reporting. So if we had positive in a manhole, we could know the building, if there are positive people, and if everything is all clear, it's all clear. And if we had positive and they didn't report, we could, this was an early warning, and we had a few incidents of that. So we divided the Technion into manholes, 11 manholes, different buildings, different number of residents. And then we did it twice a week for almost a year. And basically we got a traffic light. Here you see different days, and we could see different places that are red. And this is the whole manholes from October 20 to March 2021. And from March to June, everything was green. We didn't show it. Green is everything is okay. And all the yellow ones is things that incidents we reported and the Technion COVID committee didn't know. So by that, when they knew that something is wrong, they approached the people and asked everyone to go and be tested, and they discovered people. Some people didn't say, and all kinds of nice anecdotes, but basically people who were positive were allowed to stay in the dormitories, but had to stay confined in the rooms. And if not, it could be spread. And there was no spread of COVID in the Technion. And we didn't have any false positive. All right. And basically, once they told us that we have the false positive, but we insisted, and apparently the person with COVID went home because she felt really sick. So it wasn't false positive. And we had true positives, early warning, and this was a real success. So by that, I go on to what I'm doing now, integrated water and wastewater management for increased sustainability. I look also into between interactions of different systems. I work now on smart rainwater harvesting. How does it affect urban drainage and urban floods with model predictive control? We look at urban stormwater. Have been working almost for 2 decades on atmospheric, on gray water treatment. We look at pollutants of emerging concern, and we look at sustainability assessment for different options of wastewater, gray water reuse, and we do also work on risk assessment of if you introduce non-traditional water sources, what are the risks that you face? And I hope that I'm.
Thank you.
Yeah.
So this is something for us to thank all the speakers. Asaf have maybe a bit of time to start the discussion for this. So especially thank you for Asaf, but I will for the same everybody at the end. I prepare some slides, and with the rest of the time we'll have I think a bit of discussion about potential collaborations or how can we take all what we carry here and what you bring with you and combine with what I showed about the IIASA Water Group or maybe ideas about what we can do together in the future. But maybe we start with a bit getting to know everyone a little bit less about Sarlek, but just a little round, you can say your names, institutions, what you're doing more or less in the sentence.
Okay. Dr. Yagozi, I research at the Soil Research Station at the Ministry of Agriculture. I'm doing watershed geomorphometry, flat risk analysis, river exploration, nature distribution.
Eran from the Department of Environmental Economics and Management, the Biodiversity. I'm studying the interaction between water and economics. Developed a model of Israel's water management system. This is a dynamic model covering the entire country, taking into account the agricultural sector. It's a dynamic model. It is considered now for use by the Israeli Water Authority for its planning, guiding, as a decisions to policymaker. I think it's the missing part of my model is actually the hydrology. This is an engineering model taking into account cost and the capacity of pumping, using, delivering, extending infrastructures and so on. But with respect to hydrology, maybe there is a way to collaborate. And this is something that I think we should focus on. I don't know if tomorrow there is a meeting in Weizmann Institute.
Actually, we have a Weizmann Institute tomorrow.
You're visiting today,
Yeah,
So
tomorrow.
Oh,
Tomorrow, tomorrow they fly out, but
I think it's 4 o'clock or something like this.
it starts 4:30. I will not be fortunately I will be there 2 before.
Yeah.
maybe we have to stop them to
It's easier to start since online. It's
they can come again.
I always
I wouldn't mind.
my wife. And thank you. Since Albert is also here.
Yeah, it's just I'm not a passport, I'm the director general at IIASA, and so I'm just no water expert. I'm a fly on the wall. I'm just listening to you what the conversation is about. So trying to see how we can assist and make sure that the kinds of collaborations we'd like to see facilitate.
Actually, we have a proposal together with some from the IIASA. And
Yeah, it's in the proposals. I think it's the first stage.
for all or something.
It's a GPI and joint monitoring program on water. I think it's a risk assessment project. It's the first stage. First stage proposal, still waiting for response, but it's
Okay, so it's gone in for funding already.
waiting to know. But this is a sit down from the water group, and it's one of the partners, so he's ready to partner already.
Good. Excellent.
Hi. Michelle's BA in biology, life science faculty. Are you also associated with water? Okay.
My name is Maxen, and I'm a student for MA Migration Study.
Migration study.
Yes.
Okay. Well, I think yesterday we had another kind of event on.
Yes, I wanted to come, but I can't.
Okay. But we had Wolfgang Lutz from IIASA also was a big demographer. And we had a bit of a discussion about adding migrations into kind of future assessments or the effects of environmental stress and water scarcity on migration pressures, and then how it feeds back to population change and what does it mean then on water scarcity on the environment. It's kind of also all related, like life science and this, some engineering with biology and big data together. It's all about water, and then demography also goes in. So okay, so thank you all for coming. I put some kind of thoughts from keywords that I think if I think about what we do in IIASA. So it's about this nexus approach, all this group and the together tackling water, but not only water, but water and food, or water and biodiversity, energy, water, food, etc. And leads us to system thinking. So we don't think only about the hydrology, but we think about the management, think about the social acceptance, think about economic implication and costs. And we also saw it in the researchers presented here today. It's all applies system thinking to water. And the scale. So at least in all of our models are mostly global to regional, but we have some watershed case studies as well. At 1 kilometer, and then also maybe a multi-scale approach. So how our feedbacks of information processes effects between local to regional to global and vice versa. And then of course policy, science, and innovations. With innovation, I mean a bit also for this industry side, commercial side. So we do science, but without, for example, with what we bring, I think that's what we bring is high-tech, cutting-edge solution to create problems, but without financing, scaling it up, and coming up with a product, it won't happen. So it's all coming up together, and I think with these topics in mind, we'd like to ask two sides of questions. We'd like to reflect out and discuss it a bit. But in terms of this water group collaboration, so one of the questions would be which water groups capacities or topics, and you already commented the one, do you find interesting or aligned with your work? So similar to what you already commented on this hydrology to management model, I would like to ask other of you. And how can your specific research, even if it's not about water, can benefit from IIASA's modeling capacities or IIASA's capacities in general? This lead us back to this kind of cloud of words there. So of course, you're in the water team, but there are also other things in IIASA, and it encourage you to think beyond water here in this one. So I think the floor is for everyone to comment if you have some comments. With those.
I'd like to reflect on. I was involving a couple of months ago behind the scene about renewing the contract with IIASA. The chief scientist of the Ministry of Agriculture approached me with and as a customer. And one of the issues that came out is that the scale. Although you show that you move from very fine scale to regional and global. In Israel, most of the models and the assemblage of the models that you produce are at a very large scale that doesn't fit to the Israel reality. And even if there is one model or one component that fits to Israel scale, it's connected to another model that is working at a lower resolution. So I think this is the main issue in order to support collaboration, going down to the higher resolution that fits to Israel. because Israel is the unique lab in many cases or many characteristics, and it could be a good study for system analysis, and I think and there are many topics that are relevant to the Minister of Agriculture, but there is a gap of how to connect between what we actually need in Israel and the global orientation and the concept that IIASA is working for.
Can you just maybe provide more specific topic of research?
Well, nutrient fluxes from agriculture or the you know you kind of overview some of your models and we wish we could use them and utilize them, and but it seems like the amount of work that we will require in order to fit them to the reality of Israel makes no sense in terms of the investment of time and resources that we are lacking this.
What is your typical scale of your internal models that you find useful from your perspective?
From a watershed scale, let's say like today we are looking at just as an input as a LiDAR or some topographic scale. We are talking about sub-meters in order to hydraulically model streams and flows and in the streams and fluxes. So this is just one component. When you walk at the 30-meter resolution, is almost natural.
Yeah. No, it just give me a sense of the scale that we operate, because I think that's important for us to understand. Because I think you clearly state IIASA is stepping down in its capabilities in terms of scale, sensitive analysis for a period of time now, but we're clearly not operating at the sub-meter scale.
Maybe one comment about so it's one thing that I wanted to include in my presentation, but actually not. I don't know why. But one of the things we're also doing is kind of creating, based on sea this is just an example, we create some capacities to create surrogate models in this kind of AI deep learning models, neural networks that kind of mimic hydrological modeling. This can best be applied to any scale. So once I think this is another opportunity for collaboration, just not going with kind of conventional process-based algorithm modeling, but going with if you have a set of observation and input. So
I wrote exactly that.
Yeah. So neural networks and AI would be similar to what Asaf.
I think that the issue of scale depends on the question and the objective of our analysis. If your client is the farmer, then precise irrigation, precise application of fertilizer, and things like that. This is something that is not relevant for the farm. Okay, if you are and this farmer is acting subject to constraints, is doing the best subject to constraints. These constraints are affected by decisions of regional policymakers. Okay, and if your client is the regional policymaker, then it's not the sub-meter of the farmer within its field, but its farm. It's one of the elements in your model. So you can go to a multi-farm scale. Okay. But these regional managers are acting subject to national constraints. And if your client is the national the water authority or the Ministry of Agriculture, who are responsible for policy with respect to different management tools, it can be economic one, it can be international trade agreements, it can be bonds or on certain inputs, output constraints, something like that, immigration also, or foreign labor, then your scale is actually the different regions. So, and I'm working on the entire country level. So my element is my scale is based on regions. Okay, because this is what's relevant for my analysis. So based on this, you have to decide.
I totally agree. Yeah.
I think that it depends on what you work, as you said, but in Israel, the water in Israel is really centrally managed with it's very centralized, like many other places. But if you look at what the Water Authority does, it looks at basins, right? The Lake Inel Basin, other basins, the Western Galilee, Eastern Galilee, and so on, and they look into the basins. So you have to have the ability to look into the basins, and the basins are quite small. They are quite small. Although the question could be national, like what I've shown in the Sea of Galilee, is the government decided that Sea of Galilee is a strategic storage of water. Not only that, but all the northeastern region of the countries cannot receive water from the national water grid, thus can contribute and cannot receive. So with the droughts, there was a big problem. So you have an inter basin transfer issue, but the basins are small because the country is small, and there is a lot of diversity. So this is one thing, and the other thing I think that other work that I do, like the first one I presented, you start from a unit, and then like in city would be probably the household, the neighborhood, or whatever, and then try to build up to a holistic model. So you need the interaction between the small modules and something that overlooks over the whole system.
It just seems to me that in the water context, that Israel in particular is probably a wonderful case study to develop an agent-based model for managing water resources. And we've got quite a bit of expertise in agent-based modeling in IIASA. I think Sebastian and his group have now built up agent-based modeling for entire economies. I think the Austrian economy, for instance, as a whole, has been built up from an agent-based model, which essentially starts off at a household. Every household is an agent, and every business is an agent. Every enterprise is an agent. And the benefit of an agent-based model is the fact that you can accommodate heterogeneity between the agents. In other words, they're not seen as the average household or the average business. You can actually deal with the heterogeneity in that space, which I think seems to be critical in the space. And I think this is an area where that kind of work will come closer to the scalar requirements that I think you're talking about, and at the same time give us the heterogeneity across the landscape, and then also what it means at a national level. We build it up that way, but I think agent-based models is probably going to be very, very useful in this particular context of which you're functioning. And as a matter of interest, I think Sebastian will be working with the Japanese on the supercomputer now. There's 10 million agents in the Austrian economy model. I think they're talking about 300 million agents in the Japanese model. So it just gives you a sense of what can be achieved with computing today. So I don't know how many households you have in Israel, but if you think about the population, it's not more than 300 million.
Yeah. About probably about 2 million.
Yeah, that's what I was thinking about. So yeah, exactly. So you can actually have some really, really interesting work, and maybe there's an opportunity to bring in what the guys are doing in IIASA, which is Sebastian, to talk to the water team and speak to particularly your needs, local needs, Because I think it seems that there's a real opportunity. Okay.
I think one of the problem with this kind of meetups is that every time we come up with more ideas for new stuff and already they're quite loaded with work, but new things to do.
But the point is, I mean, and this is the idea, is that one has to, in the same way that you've done now, we need to write the proposal and then go and find the funding.
Yeah.
You know, and once the funding is there, then it can happen, and we can bring in the resources to help us. Because I think it's not like you can expect people to pull the money out of the back pocket. It's not going to work that way for anybody involved.
I
would like to add on. Thank you. So one of the dimensions that, so I'm not an expert in modeling, but what it presented is a few things. First, when you discussed about the modeling about wastewater, you talked about wastewater that you know the borders, you know the treatment plant, it's treated, collected, but in the work, for example, that we're doing, I'm not sure that it be connected to modeling, but the wastewater is actually discharged or in ponds or in different scenarios, which is much more complex. And also the farmers are small farm holders, so they have like acre area of farming. Maybe it's similar to the Israeli case, but the wastewater situation is definitely not similar to the Israeli case where we know where the wastewater goes and how it's being collected and stuff like that. So for example, if it's possible to also add the incidental wastewater generation also in the village location or at the community level, that would also be interesting. In addition to that, those models do not integrate water quality. So for example, there are issues with fluoride, arsenic in groundwater. So how can it also connect to water quality or also biological contamination, as we discussed, and not only nutrients. So, and so this is also something that I saw that is not being integrated within these models. And like the scale down, like you discussed, so in the areas that we're working, it's villages, it's households, it's the safety of the water at the household level. Like I said, that every household could be an agent. So if we have a water quality analysis across small locations and stuff like that, how can we integrate that into the models? Because at the end, if there's decision making there, is it only fit to developed countries, these models, or do they also look at situations where not all the sewage is collected? So that's kind of like things that I didn't get from your discussion. So I can maybe comment because I already have quite a few comments I have another slide. We'll start from the last one. So about the model, basically the models are first modular, so we don't have to go kind of forward with all the options, and we can control the options. The waste, specifically the wastewater treatment model, which we're working on the publication now for it, has inputs there. And so the generated wastewater is simulated in CLM, and we can control it with other inputs. But the wastewater treatment plants are in input there. Currently, we just have two technologies, so extensive, more like this pond thing, and intensive. But this is open source development, right? I already commented that I should talk to you about what you presented and taking to see more scale percentage. That would be interesting. Yeah, I think so. But yeah, if it's very customized, it can change, flexible, can be changed easily. If it different circumstances, definitely not only for developed countries. The country, I think it is more oriented for developing countries, and most of the projects are in India, Sub-Saharan Africa,
like Victoria.
Yeah, like Victoria Basin that we showed project in China. It's like mixed, but also we have projects in Norway, Austria, so it's kind of diverse. And we have applications for it now. Take me to the next one. So about Israeli hydrology, scale issue. At least for the hydrological side, we already have one success for the Eran basin, which is one of the bigger basins in Israel. Big as a the hydrologists say it's like it seems looking at the discharge data, it seems like it's just like just a few flashes of the toilet because he used to work with the Amazon basin and the Mekong and like this huge river, and then Israel is very small. And then the model is also highly sensitive for any kind of error or thing that are included. So we did have put a lot of effort in developing things that we think are critical for Israel, like wastewater collection and reuse, like moving water around, including desalination in Israel, which on the slide, desalination. And to the very technical thing like capturing water in a reservoir in the river, like in Sorek. So we have this wastewater from Jerusalem, treated to secondary level, sent to the river, flown down and captured in around Shemesh. And they pump out and go for irrigation in Lachish. So all these kind of systems are captured within the model with minor to big developments. And then this level of flexibility with the modular approach, with the open sourceness and Python program, like basically easy, quite acceptable language that we've written in, allow us to customize the model to the needs of the project. Another important issue is scale, because Mark also mentions is agent-based modeling. So one of the challenges with the scale model that they showed was that our CBOTM hydrology works at 1 kilometer, but farms that are the agents are much smaller. So within this specific agent-based, this APM, we have a nested kind of modeling approach, which farm owners, these farm plots are modeled as kind of hydrological response units. So the intersection between the grid of CBOTM, which is basically 1 kilometer, and the ownership on land and management of the farms. And each of these hydrological responses make decisions, sends water demand, get its own soil moisture simulated, and then it sends it back to CBOTM, which works in the 1 kilometer, and they communicate. Results are quite nice. So just to sum up a bit, we already kind of targeted models for business except the hydrological side. When we have this water quality model in place, and we hope to also include other content in the polyforms in the future, but we start, due to the case that we start with nitrogen phosphorus. And water quality is much trickier in terms of getting it right, in terms of driver, in terms of resolution. So we don't expect like the similar results as the hydrology, but we hope the good results in the comparison. So we know later about it. Yeah, and it's customized, so it doesn't have to be the current model, but if I think the next point for this one is I think I can just encourage researchers, policy makers, official researchers in government to maybe address us directly. So yeah, you can write us through the website and just with the emails. Just write to us. We can sit and talk, like online meeting. Sit and talk. You say what you need, what you have in mind, and we think together our solution. But you don't have to do yourself. Develop one project. Either funded by government funds, either funded by competitive like research foundations. Once we have it, we do the necessary developments for the project to work, and this is actually how CBOTM is developed. It's a core model, but then every model is coming from different projects. And I would actually be very interested in see first the full Israel hydrological model for CBOTM. Because we have just for 2 basins. This is quite massive collaboration with kind of data acquisition. And also,
but on the other hand, I don't need any meter there to be modeled. Any meter, any square meter.
No, even for the 1 kilometer.
I'm working on big scales, so on the level of aquifers.
We can discuss the details. I would like to see an Israel scale model that has other potentials than water, like we think of geopolitics and Israel, and like maybe just regional
just the neighbors
Yeah.
and what the consequences are. Because I think
water
that's important.
scarcity in Jordan.
Because that, again, that comes up to, it comes to other issues. By understanding not only the Israel situation, but understanding what's happening around Israel, we have a better understanding as to what it means in terms of migration pressures and other things in the context of climate change in the future. And so you can start anticipating some long-term consequences, and what if scenarios, that you can start exploring the food insecurity issues and how that's going to affect the region and the pressures that may come back to Israel as a consequence.
I think maybe just another point is that I think I would be happy and probably other people to have the online talks specifically about like the wastewater project, and then maybe to the group, and then we can discuss in details what you think is missing and what we can do better to include it with the second module. This for everyone. Thank you.
All right, guys.
Just one comment.
Yeah. Standard.
So I see this, welcome, yeah. Yes.
Not sure. Okay. As a matter
One small comment. From your presentation, I got the impression that you have big models that integrate a lot of data. But what I didn't see, I think, or I didn't understand, is the connection to policymakers. Can your big data and analysis are oriented for policy making? I'll give you a small example. Last week, the Water Authority decided to increase the water prices for agriculture by 30%. What is the implication on the farming sector? What is the implication on the development of the water system for a long time? Will it, if the agriculture takes less water? What is the route of development of the pollination plants in Israel? And so these are questions that I think you have to ask yourself whether you can answer them and support policymakers in different levels.
First question, I think yes, I can ask and answer. Have you have any question in mind? I think what it requires mostly is more introduction between policy makers, policy officials, and ourselves, and maybe removing a bit of these skepticism about these large-scale, downscale issues, because we can manage them to specific questions. Sub-meters, maybe not with this model, maybe other tools, but if we put the questions and not like a scale, questions on the table, we can discuss what are the right tools, we can manage them. I think only with my work in Israel, which turns out quite restricted due to collaboration issues. There are many potentials, just for example, desalination you mentioned. So I am interested to know whether the caps of desalination in the contracts are optimal or not. So we have to buy specific amounts, like a target price specific amount with CPP data. But maybe if you go back just a month, probably the next one, which I already signed, maybe you can ask yourself, we are vanished.